Okay, so the fourth topic to be discussed during this course is games with simultaneous moves under mixed strategies. So, what does mixed strategy mean? In pure strategies, the players have to choose their strategies, with full determination, or let's say with 100% probability, either DL or CC for sure. However, there is no guarantee that following pure strategy will result in any Nash equilibrium. For instance, you can take a look at this game. In this case, the players can actually randomize, so assign some probabilities to their possible actions. So for instance, instead of choosing just DL or CC, Evert might say that for her, optimal strategy is to choose DL with 60% probability and CC with 40% probability, and then just choose randomly. I don't know, like putting 6 black balls and 4 white balls into the bag and pick just one, to see what strategy she shall actually undertake. So how to define the optimal, probability assigned to each strategy? You have to start with assigning probabilities to the player's possible strategies. So let's say here that Evert will choose DL with probability P. Evert will choose CC with probability 1 minus P, since we have only 2 possible strategies for Evert. Navratilova will choose DL with probability Q, and CC with probability 1 minus Q. The next step is designing expected payoff functions for each player. So, as you remember, expected value is just product of possible outcome and probability assigned to this outcome. So we do this in the same way. So Evert can get 50 with probability Q times P, because it depends both on her strategy of choice and Navratilova's strategy of choice. So here you've got P times Q times 50. Evert might get 80 with probability P times 1 minus Q. And then expected payoff for her is 80 times P times 1 minus Q. You have it here. Evert can get 90 with probability of Q times 1 minus P. Here you have it. And finally, she can get 20 with probability 1 minus P times 1 minus Q. We do the very same analysis for Navratilova, who can get 50 with probability P times Q, 20 with probability of P times 1 minus Q, 10 with probability Q times 1 minus P, and 80 with probability of 1 minus Q times 1 minus P. Here you have this function. So I believe it's clear. So let's start our analysis with Evert. This is her expected payoff function. So by doing some basic mathematical operations, you can simplify this to this form, because on this part you have P at the common multiplier, and in this part you've got 1 minus P at the common multiplier. Then you open the brackets, to get basically the value of intercept, because it does not contain any P element, plus P times some expression. So keep in mind that P is the probability of Evert choosing DL. Evert has no control over Q, because it will depend on the decision of Navratilova. That's why we take Q as some exogenous parameter, and we treat P as an endogenous parameter, so some variable which is under the direct control of Evert. So when you simplify this should be your final solution. It's 70q plus 20 plus p times, some coefficient. So here you've got this intercept, and actually the slope of the function would depend on the value of this expression, I mean 60 minus 100q, and to be more precise, it will depend on the value of q. So there are two possible options. If 60 minus 100q takes a positive value, which implies that q takes the value below 0.6, then the slope of this function is positive, which means that expected payoff of Everett increases as probability she chooses DL increases. If the value of this expression is negative, meaning that q takes the value above 0.6, then increase in p will result in decrease of expected payoff for Everett. Finally, if the value of q takes exactly 0.6, then Everett is actually indifferent. So I believe it's clear, so we can proceed with best response analysis. So best response function tells you what should be the optimal value of p depending on the strategy undertaken by Navratilova, q. So what should be the most adequate response of Everett depending on any possible value of q. So take a look here. If the value of q is below 0.6, then higher value of p is associated with higher value of expected payoff for Everett. So basically, if q is below 0.6, then Everett, as the rational player, has to keep her p as high as possible, because in this case, higher p means higher expected payoff for her. So here we have it. However, if the value of q exceeds 0.6, then any increase in p will be associated with decrease in expected payoff for Everett. So then Everett has to keep p as low as possible, basically equal to 0, because probability can yield the value between 0 and 1. Finally, again, if it's exactly equal to 0.6, she is indifferent. As the result, here is best response function for Everett. Now we can do the very same analysis for Navratilova. So here is the expected payoff function of Navratilova. Again, you do those basic algebraic operations in order to get a linear function. So this part does not contain any q. This is basically just the value of intercept. And this is the coefficient of q, 100p minus 70. Analogously, if 100p minus 70 takes a positive value, meaning that p exceeds 0.7, then any increase in q increases expected payoff for Navratilova. If 100p minus 70 takes a negative value, meaning that p is below 0.7, any increase in q results in the decrease in expected value for Navratilova. So now, as the rational player, when p is below 0.7 here, it means that increase in q decreases her expected payoff. So as a rational player, in this case, Navratilova should take her q as low as possible, and in our case it's 0, because again, probability can take the value between 0 and 1. If p exceeds 0.7, so we are located here, then any increase in q will increase expected payoff for Navratilova. So as a rational player, Navratilova will have to keep her q as high as possible, and this is what you've got. Finally, if it's exactly equal to 0.7, she is basically just indifferent, and we depict this fragment. Okay, so this is best response function of Evert. This is best response function of Navratilova. How can you analyze this? So basically what you have to do is to depict these two functions on the same graph. So basically you just have to invert either best response function of Evert or best response function of Navratilova. So here we do this for Navratilova, and take a look. If P is between 0 and 0.7, this fragment of her best response function is just located on p-axis. So here is p-axis, and here is the fragment located on p-axis. If the value of p is equal to 0.7, then her function goes parallel to q-axis. Here you have it. And finally, if the value of p exceeds 0.7, the function goes parallel to p-axis. Here you have this segment. So as a result, on the intercept of two best response functions of these players, we have a Nash equilibrium, by definition, you know, because Nash equilibrium occurs when two players play their best strategies. Because again, this is the best possible strategy for Evert and the best possible strategy for Navratilova. When two players play their best strategies simultaneously, keeping in mind other players do the same. So basically, here you have it. So in equilibrium, Evert should choose DL with probability 0.7, and Navratilova should choose DL with probability 0.6. Okay, so actually there are some alternative methods to define the optimal mix. So what you can do, for instance, is to apply first order condition to maximize the expected payoff for Navratilova and Evert. So in this case, you have to take the partial derivative of Evert's payoff function with respect to p. Because again, for Evert, Q is some exogenous parameter. So she has a control only over P, her own probability of choosing DL. That's why you have to differentiate with respect to P. For Navratilova, it's just the opposite. So in this case, actually, you have to differentiate with respect to Q, because Q is the variable under Navratilova's control. So when you do this, you will actually see that, applying first order condition gives you the same result as equalizing expected payoffs associated with different strategies for these two players. So here, for instance, if Evert decides to play DL, then her expected payoff of DL is equal to 50 times Q plus plus 80 times 1 minus Q. And here you have it. So you can do the same in order to define the expected payoff associated with CC strategy for Evert. And, when you equalize them, basically making Evert indifferent between those two strategies, it will be just the same as what you've got when applying first order condition for maximization. So the result is that Q is equal to 0.6. You can do the same analysis for Navratilova, getting P equal to 0.7. Okay, so actually when it comes to mixed strategies, the notion of the Nash equilibrium is a bit problematic. So based on the example we have just discussed, when Evert plays her best strategy, then Navratilova is indifferent between DL and CC. in this case, there is no incentive for Navratilova to mix. She's basically just indifferent between those two strategies. So she has no incentive to mix. She can just, simplify her life and play the pure strategy. However, if both the players follow the same logic and just shift to the pure strategy, it means there is no Nash equilibrium at all. So that's why, even though the notion of the Nash equilibrium is a bit problematic under the mixed strategy, it can still be, let's say, legitimized by the fact that this is the only way, at all of defining Nash equilibrium in this case. So, in this case, you remember we discussed the example of Harry and Sally when we analyzed assurance games with multiple equilibria. Nash equilibrium can also provide some solution to this kind of problem. So, as you remember, we have two Nash equilibria in pure strategy when Harry and Sally meet in Starbucks and when Harry and Sally meet at Costa Coffee. However, actually, it's hard to say what would be the exact solution to this game, and which strategy each of the players shall undertake. So in this case, actually, randomization might be a useful tool, just providing some insight in how these problems are solved in real life. So here, basically, you just do the same. Let's start with Harry. So for Harry, the expected payoff will be equal to 1 times P times Q plus 0 times times 1 minus Q times P plus 1 minus P times 0 times Q plus 1 minus P times 1 minus Q. Yeah, so I believe in this case I already simplified this expression, just for P and 1 minus P terms. So expected payoff for Harry associated with Starbucks and expected payoff for Harry associated with Costa Coffee. So for Sally, you just do it analogously. So for Sally, expected payoff associated with Starbucks is equal to 1 times P times Q plus 0 times 1 minus P times Q, what you've got here, plus 1 minus Q times P times 0, plus 1 minus Q times 1 minus P. Yeah, this is what you've got here. Okay, so for Harry, we've already defined the expected payoff function. And when you simplify, it will give you 1 minus Q plus P times 2Q minus 1. So again, if Q exceeds 0.5, then expected payoff for Harry will increase as P increases, because this coefficient will take the positive value. If Q is less than 0.5, then expected payoff for Harry will decrease as P increases. So there will be an inverse relationship between P and expected payoff, because this coefficient will yield a negative value. So again, as a rational player, if Q is low, so the probability that Sally will go to Starbucks is low, then for Harry, the probability of going to Starbucks should be as low as possible, just based on this logic. Because again, when Q is smaller than 0.5, there is an inverted relationship between expected payoff and P. That's why rational Harry should keep his P as low as possible. Analogously, if Q exceeds 0.5, then increase in P will be associated with increase in expected payoff for Harry, so he should keep P as high as possible. Again, you can also apply ordinary human logic to analyze this case. So if the probability that Sally will go to Starbucks is lower than some critical value, then Harry should not go to Starbucks either, it would be better to go to Costa Coffee, because then it's a higher probability of meeting Sally. And vice versa. If probability that Sally will go to Starbucks exceeds some critical value, then for Harry it also makes sense to go to Starbucks instead of Costa Coffee. Okay, I hope this is fine. So here you can do the very same analysis for Sally, just analyzing her expected payoff function. When you solve this and simplify, you should get this. Again, remember that in this case, P is an exogenous parameter and Q is an endogenous parameter, because Q is under the direct control of Sally. So then you will see that if P, probability that Harry will go to Starbucks exceeds 0.5, then expected payoff for Sally will increase as... Okay, actually here it should be Q, sorry. Okay, then expected payoff for Sally will increase as Q increases. So, if Harry rather decides to go to Starbucks, then it makes sense for Sally to go to Starbucks as well. And if probability P is smaller than 0.5, then for Sally, expected payoff will decrease as Q increases. So again, if Harry decides rather to go to Costa Coffee, then it makes no sense for Sally to go to Starbucks. So using the same kind of analysis, if P is less than 0.5 here, then it makes no sense for Sally to choose high P, because in this case, any increase in Q... it makes no sense for Sally to choose a high Q, because in this case, any increase in Q will be associated with decrease in expected payoff for Sally. And if P is above 0.5, then increase in Q will be associated with increase in expected payoff for Sally. So she would rather choose Q as high as possible. And again, if P is exactly equal to 0.5, then she is just indifferent. Okay, so here we've got two best response functions for Harry and for Sally, and we have to combine them. So you see that if P is below 0.5, then for Sally, best response function goes just along the p-axis. So this is what we've got here. Oh no, sorry. Actually, this time I did it for Harry. Doesn't matter. So if Q is below 0.5, then for Harry, best response function goes along the q-axis. This is what you've got here. Then, when Q is equal to 0.5, it goes parallel to p-axis. Again, parallel to p-axis. And finally, if Q exceeds 0.5, it goes parallel to q-axis. Here, parallel to q-axis. As a result, we have three intercepts, which makes sense. So, there are three equilibria possible. First, when both of them decide to go to Costa Coffee. So for Sally, probability of going to Starbucks is equal to 0, and for Harry, probability of going to Starbucks is equal to 0. Then you have an equilibrium when both of them decide to go to Starbucks, with probabilities assigned to this strategy equal to 1. And finally, we have one more Nash equilibrium in mixed strategies when they randomize. So when for each of them, the probability of going to Starbucks is equal to 0.5. And yeah, so each time when you define equilibrium in mixed strategies, and there are some Nash equilibria in pure strategies, it should be also visible on your graph. I mean, on the graph with best response functions. Actually, it makes sense because keep in mind that in case of Navratilova and effort, we had no equilibrium in pure strategies. So only equilibrium in mixed strategies is possible. That's why we have only one point of intercept of their best response functions on this graph, which I believe should make sense. Okay, consider another example. Let's just call it game with assurance. When both for Harry and Sally, an equilibrium associated with meeting at Costa Coffee gives higher payoff than equilibrium associated with going to Starbucks. So analogously, you define their expected payoff functions. Now you just replace, here you've got 2 multiplied by 1 minus p, 1 minus q. Analogously, it goes for Sally. 2 times 1 minus q times 1 minus p. Okay, makes sense. So you just do the same kind of analysis. You will see that if q exceeds 2 over 3, then any increase in p is associated with increase in expected payoff for Harry, and vice versa. If q is below 2 over 3, then for Harry, expected payoff decreases as price increases. So if q is below this critical value we have just defined based on the value of this coefficient, then there is an inverse relationship between p and expected payoff. So for Harry, in this case, it makes sense to keep his probability of going to Starbucks as low as possible. And the lowest possible value is 0. So if q is equal to 2 over 3, he is indifferent. Finally, if q exceeds 2 over 3, then increase in p is associated with increase in expected payoff for Harry. So it makes sense to keep p as high as possible. Now consider the same example for Sally. Here is your expected payoff, some basic mathematical operations, and this is what you should end up with. So once again, for Sally, p is just some kind of exogenous parameter. So if p exceeds 2 over 3, then expected payoff for Sally will increase as q increases. So it makes sense to keep it as high as possible, and vice versa. If p is below 2 over 3, then increase in q is associated with decrease in expected payoff for Sally. So it makes sense to keep it as low as possible, and if p is equal to 2 over 3, then she is indifferent. Once again, you combine those two graphs. So you combine those two graphs, and this is your solution. Okay, actually in this time, for some strange reason, I decided not to change the color, but I believe it will be clear for you. So in this case, this was best response function for Harry, this was 1 for Sally, and in this case we inverted function for Sally. So once again, you will see that here we have 3 Nash equilibria. When they meet in Costa Coffee, and for both of them probability of going to Starbucks is equal to 0. When they meet in Starbucks, and then probability of going to Starbucks is equal to 1. And here, when for each of them probability of going to Starbucks is equal to 2 over 3. So actually this is kind of counterintuitive, because take a look here. It's clear that they both prefer meeting at Costa Coffee. So why, should they decide to go to Starbucks with higher probability? So yeah, although this is kind of counterintuitive, it will make sense if you recall that for each of them, the main objective, like the key to defining the optimal mix, is to keep the other player indifferent between going to Costa Coffee and Starbucks. So if Harry shall be indifferent between going to Costa Coffee and Starbucks, then probability assigned to going to Starbucks should be higher. because this one yields lower payoff, also resulting in, so this one yields lower payoff. That's why to have equal expected payoff, the probability assigned to going to Starbucks should be higher than one assigned to probability to going to Costa Coffee. The same applies to Sally, She definitely prefers Costa Coffee, but Harry would like to have her expected payoff from Costa Coffee equal to expected payoff of going to Starbucks, and since this one yields lower payoff, it should be assigned a higher probability, just to have those expected payoffs equal. So I know that this is counterintuitive, why assign higher probability to the place you probably like less than the other place. However, it will make sense if you recall that the key concept of this is to keep the player indifferent, between two possible outcomes. Okay, so there is some alternative method of solution. In this case, you can just equalize Harry's expected payoffs associated with going to Starbucks and Costa Coffee. It will give you the same outcome. And you can equalize Sally's payoffs associated with going to Starbucks and Costa Coffee. And you will see that in order to keep her indifferent, Harry has to choose probability of going to Starbucks equal to 2/3. So okay, we are gonna apply this method with the next game. So this is a chicken game. As you remember, we have two equilibrium solutions in pure strategies: when James swerves and Dean goes straight, or when James goes straight and Dean swerves. So again, it's really unclear what would be the solution, and in this case, randomization might be a useful tool for both of these players. So James will be indifferent between going straight and going swerve if his expected payoff associated with going straight, like -2 times q plus 0 times 1 minus q, will be equal to the expected payoff associated with going swerve. So 0 times q plus 0 times 1 minus q. Dean is indifferent between going straight and swerve when his expected payoff associated with this strategy is equal to the expected payoff associated with this strategy. So here we've got -2 times p plus 1 times 1 minus p should be equal to 0 times p plus 1 minus p times 0. Again, in this case, you look at the probabilities assigned by the other players. So in equilibrium, you would like to keep the other player indifferent between two possible strategies, which implies equalization of the expected payoffs associated with each strategy. So when you apply this method of solution, you will see that in equilibrium, q should be equal to 1/3. So Dean's probability of going straight should be equal to 1/3, and probability of swerving should be equal to 2/3. And James' probability of going straight should be also equal to 1/3. Again, in this case, I skipped all the steps with drawing best response functions because I believe at this point you can do it yourself. So in this case, we also have 3 Nash equilibria. So this is the first Nash equilibrium in pure strategies. So it happens when Dean's probability of going straight is equal to 1 and James' probability of going straight is equal to 0. So less formally, it happens when Dean goes straight and James swerves. Here. The second one occurs when James decides to go straight. So his probability of going straight is equal to 1, and Dean's probability of going straight is equal to 0. So James goes straight and Dean swerves. So finally here you have the intercept. And again, you can also analyze those best response functions using ordinary human logic. So let's say, okay, here. So we analyze how Dean should make his decision based on the decision made by James. So in this case, let's say that probability that James will decide to go straight is below some critical value. So then it makes sense for Dean's to just to go straight, because in this case he would prefer to go straight and win over James in this game. So, however, if James' probability of going straight exceeds this critical value, then probably James will decide to go straight, and then for Dean it makes sense to swerve, because again in this case it will just mean if James decide to go straight, then Dean shall rather swerve, because then it will be associated with higher payoff for him. Analogously, you can do the same analysis for James. Okay, so that was it. I will publish some exercises on the subam, and next time we're gonna to discuss in details how to solve these exercises. So that's it, and thank you for your attention.